A kid stands at one end of a floating canoe and walks to the far end. The canoe slides backward beneath them, though nobody pushed it. Why? Because nothing grips the boat sideways, so the boat and kid together can't shift their center of mass. Now the real puzzle. Problem 1 of the 1971 International Physics Olympiad. A wedge sits on a slick, frictionless floor. 2 blocks tied by a string over a pulley at the top rest on its 2 faces. Let go, and the blocks slide, but watch the ramp itself. It drifts too. The one number we're after is capital A, the acceleration of the wedge. Which way does the ramp go and how fast? Or could everything just stay perfectly still? Most people picture a heavy ramp that holds put while the blocks slide on it. Hold that guess. Our job is one number, capital A, the acceleration of the wedge. Before any algebra, a choice of weapon. You could draw forces, but look what you are up against. The ramp is accelerating, so its frame isn't honest. There is a string tension, 2 normal forces, and 3 bodies to track. Is that really how you want to spend an hour? So we won't draw a single force. We'll use the Lagrangian, write the system's energy, and the equations of motion fall out. The recipe never changes. Coordinates, kinetic minus potential energy, Euler-Lagrange, then solve. And the whole setup needs just 2 numbers. Capital X, how far the wedge has slid, and S, how far the blocks have moved along the faces. The string locks them to a single S, 2 coordinates, and the state is fully pinned. Here's the physical intuition in one picture. Draw a box around all 3, wedge in both blocks, and mark their shared center of mass. Nothing pushes this whole system sideways. The frictionless floor can only push up. Gravity only pulls down, so that mark cannot drift sideways ever, and that hangs on the floor being frictionless. Add friction, and the trick breaks. So before I move anything, if block M1 slides down to the left, which way must the wedge go? The wedge slides right just enough to hold the center of mass on its line. Now you might object, I am not pushing the ramp, so why would it move? You are not, the blocks are from the inside, and the only way to keep that center fixed while they slide is for the wedge to recoil. So the ramp does move, the blocks shove it from the inside. Keep that. We still owe you which way and how fast. Step 1, positions. Slide a block a distance. As along a face and project it as cosine alpha sideways, as sine alpha up or down. So block 1 sits at x minus s cosine alpha 1, dropped by s sine alpha 1. Block 2 keeps the same x but rises by s sine alpha 2. Differentiate in time, and each block's speed squared falls out. The wedge and the slide cross-coupled by the cosine of the angle. The kinetic energy is 1/2 mx dot squared, plus each block's half mv squared. Now substitute those speeds and collect. The v's are gone, t reads in x dot and s dot alone. An effective inertia, a coupling in the slide. And the potential energy is just gravity times the heights gs times m2. Sine alpha 2 minus m1 sine alpha 1. Quick one. Energy always wants to drop. Which way does the system slide to lower this potential? Subtract them. The Lagrangian L equals T minus V. Drop the 2 expressions in, and this one line holds the entire physics of the problem. Here is the very same Lagrangian we just built. On the picture, capital A is the wedge's acceleration, the one we want, and lowercase a is the block's common slide along the faces. Now turn the crank, Euler-Lagrange. Once for x and once for s. One equation from each. Look hard at the Lagrangian. X dot appears, but a bare x never does. So what is x commit? A conserved quantity, that first equation is the recoil relation. Capital A driven by lowercase a. And it is exactly momentum conservation, the canoe written in algebra. The S equation is the second, the drive gravity sign imbalance. M1 sine alpha 1 minus M2 sine alpha 2 is what pushes the blocks to slide. And notice what never showed up. No tension, no normal forces, no fictitious forces. A force treatment needs all three. The Lagrangian just skipped them. Two equations, two unknowns, the wedge's acceleration, capital A, and the block slide, lowercase a. No physics left, just algebra. Solve the first for the slide, drop it into the second, and lowercase a cancels. Capital A assembles itself. Before I read it off, look at the top. When is capital A exactly 0? Gravity times the cosine sum, the geometry times the sign imbalance. The drive all over an effective inertia. Sines drive, cosines couple, the bottom resists. And A is 0 exactly when the two sine pulls balance. Real numbers, a 4-kilogram wedge. On the left, 2 kilograms at 30 degrees. On the right, 1 kilogram at 45. The drive 2 times sine 30 is 1. 1 times sine 45 is about 0.7. The left block wins. The cosine sum is about 2.4. The effective inertia, about 15. Put it together. Capital A comes out at very nearly 1/2 a meter per second squared to the right, away from the block that is winning. There's that first question, answered with a number and a direction. And the second nudged the right block to root 2 kilograms. So both sides pull with exactly 1, the sign imbalance vanishes, and the whole assembly locks in place, though nothing holds it. The acceleration of the wedge from 10 DIT never moves to one honest formula. So describe it with just 2 numbers. Write down its energy and the equations of motion fall out. Nothing pushes it sideways, so the ramp recoils. And which way depends on which slope wins. Remember it is slide. Set the state 2 coordinates, x and s. The Lagrangian kinetic minus potential. The inextensible string ties the blocks to one slide. The drive is the sign imbalance, and Euler-Lagrange turns the crank to the answer, capital A. One last thing to chew on. What if the flaw weren't frictionless? Would the trick still hold?